Okay, so the second and last example of this form, I'm actually taking an exam question because the new exams, they are producing questions in slightly harder fashion, but it's exactly the same. So I'm going to talk through this one so you can see how it might come up. Okay, just so you're aware, it's very long. So we've got all of this, we've got part III and IV, and it goes all the way up to 7 parts over on this side. Okay, so let's start with the first part. So the intensity of the sun's radiation, y, and the average distance from the sun is x, as shown for Mercury and Jupiter below. So we've got x, 2 values, and we've got y, 2 values. The intensity y is proportional to a power of the distance x. Now this is using what you should have drilled in from you from GCSE. So it says write an equation for y in terms of x with 2 constants. Well, let's read this line here. Y is proportional to a power of distance x. Now when something's proportional, we should think straight away y equals k timesing by whatever it is now, power of a distance x, let's call that x to the power of n. Okay, which most of us usually just write as y equals k, x to the n. Okay, now it says show that the equation can be written in the form ln y equals a plus b ln x. Now, I'll make a note straight away. I chose k and n in mine, and that's very normal to choose. At some point, I'm going to have to show how I'm replacing k and n with a and b of some form. So let's work through this and start off with y equals k x to the n. Now we know to get something of this form, we're going to have to take logs of both sides. Let's note that they're using the natural logarithm here. So I'll take ln on both sides, and I'll say that ln y is equal to ln k of x, n, all of that in brackets. Okay, so now we use the product rules. We're going to say that we can add k and x to the n with ln separately. So I've got ln k plus ln x to the power of n, and then we'll use our power rule. So I get ln y is equal to ln k plus n ln x. Now I'm ish happy because I've got my ln y, I've got my ln x. However, I want a and b to be different. So I'm just going to say if ln k is equal to a, now that's allowed because k is just a number, ln k is just a number. So we'll just say that ln k is the value a and n will be the value of b. This means I get that ln y is equal to ln k, which is a, plus b ln x. Okay, and all you do is just redefine in terms of a and b, and that's allowed. So easiest part of the question, it actually says complete the table below, correct for significant figures, and this was an insert. Okay, so I just want ln x and ln y. Now I can see up here, x is 0.3075. Okay, so if I put that into my calculator, the x value there, I'll be able to fill this in here. It says 4 significant figures, so I'll leave it as negative 1.179. Okay, I'm going to do the same for the next ones. These 3 spaces. Okay, so I can see that ln of 14,400 is 9.575. ln of 4.950 is 1.599 to 4 significant figures. Finally, ln of 55.8 is 4.02. Now that 7's going to round to 2. Okay, now what we have here is, I know that in real life I'm finding k and x through lots of practice that you'll get when we plot, I'll write this down here, and I'll do it here. When we plot ln x against ln y, I will get a straight line. Okay, so we know that we only need 2 points to find a straight line. We need the change in y divided by the change in x. So we're going to use this to find the values of a and b. So let's remind ourselves looking at this. So b is going to be the gradient, okay, which is the change in the vertical, which will be in ln y, divided by the change in ln x. Okay, so if I write that up, I'm going to go 9.575 goes down to 4.022. and the x is negative 1.179, take away 1.599. Now, as it says using the values in III, they're expecting to use these rounded values, so be careful here. So when I've done this on my calculator over here, I can see that the value of b is going to equal negative 1.999. I'll do it to 4 significant figures as well. Okay, and that's there. So there's our gradient, and we now go on to think that a, I'm going to write it straight there so I don't run out of space, is the y-intercept. Okay, so I'm going to use that. I know this is the general rule, and I'm going to input some values, remembering to use the x that connects the y. So I'll use the first set of values. It really doesn't matter which one you use. So I'm going to say that 9.575 is equal to a plus b, which is negative 1.999, times ln x, which linked to that value is negative 1.179. Okay, if we rearrange that, well, if I multiply those numbers together, let's do negative 1.999 times negative 1.179. I get 2.356821. So I find out that A is 9.575. Subtract this answer, and I find out that therefore A is equal to, let's say, 7.218. Okay, so there's the answer to that question. B is negative 1.999 and A is equal to 7.218. So now it says, hence rewrite your equation from part I. So let's just go back to part I. This is my equation here, so I'm just going to write that out. So I get that y equals k x to the n. Okay, and I want to rewrite this equation now. Now I'll go here and see this thing here, that ln k is equal to a and n is equal to b. So let's start with n will be equal to b, which I can say straight away is just negative 1.999. Okay, I don't need to do any work for that. It is just there. However, I will have to do work when I say that ln k is equal to a. So I need to do a little bit of work with this. So that means that ln k is equal to 7.218, which means that k will equal, the base of this is e, so e to the power of 7.218, which if I use my calculator, I get 1,364. Let's do that to the nearest whole. Okay, so let you think if you have any questions. So if I'm rewriting this equation here, that means I'm going to get that y is equal to k, which is 1,364, times x to the power of b, which is n, which is negative 1.999. And there's my answer. Okay, going on to sketch a graph of the equation found in part V. Now what I'm personally going to do here is I'm going to say, well, if I've got y equals 1,364 x to negative 1.999, I want that to be something more familiar to allow me to sketch it. So I'm first of all going to think of that as equal to 1,364 over x to the power of 1.999. So this is going to be similar to a y equals 1 over x squared graph. Okay, now just a reminder, y equals 1 over x squared looks something like that. Okay, now because x is a distance from the sun, x can't be negative, so I'm not going to be bothered about this side here. So my sketch is just going to be a stretch of that curve there. So if I say that sketch a graph of the equation, if this is what x and that is y, it's going to have this sort of form. Okay, it's going to be super stretched, but we don't need to show any values. Okay, the important thing is I've got an asymptote at y equals 0 and at x equals 0. Okay, so the x-axis and the y-axis. Okay, final part. Now this part comes up a lot. It's just an application of the equation. Earth is 1 astronomical unit from the sun. Now if I take you back to the question, we had that it was x astronomical units and it was y watts per meter squared for the sun's radiation. So if Earth is 1 astronomical unit, this means that I've got that x is equal to 1, and I want to find the intensity of the sun's radiation. Find the intensity of that means I want to find y. So I'm going to say that y is equal to, go back to my equation, 1364 multiplied by x value, 1 to the power of negative 1.999. Well, 1 to the power of anything is just 1, so that means the intensity of the sun's radiation is 1364, and it was in watts per meter squared, or per square meter. And that's it. Okay, so that's a really difficult, but hopefully you can see how it's linked to that same idea, and there's nothing new. It's the same concept as the last example. Let me know questions. There is lots for you to have a go at purely based on this now.